Hi, so this is a second video on the mechanical model of the atom, and on this part of the video, we're going to be talking about electron configuration, how you draw the electron configuration diagrams. So in this case, earlier in the part one of the video, we talk about how we change from the Bohr model of the atom all the way to the all the way to the quantum mechanical model of the atom. Okay, we talk about all these changes and all these discovery within that one and a half 2 decades, and how it changes our understanding of the atom. So we're going to talk about at this point. We're going to talk about electron configuration. Okay, so electron configuration. You're talking about really where are these electrons when you are in an atom. Okay, now we know that we can't exactly know where each the exact location of an atom, but we have a good guess. We have a good idea where they are, up to 90 or 95% of chance correct. So we're going to talk about where they are in the different orbitals. Okay, now just like earlier we talk about, oh yeah, you have different shells. Okay, you have different shells, and you also have different subshells. Okay, so in this case, we're going to talk about how do we actually fill up the different orbitals. Here are a number of rules, as you can see. We're talking about, for example, this principle. You kind of follow that too when you learned how to draw the Bohr-Rutherford diagram. So you put the electrons on the lower shell first before you draw on the other shells. Is the same rule, still applies. Um, the other thing is, for example, Pauli exclusion principle. So each of these orbitals, or each of these little slots, orbitals have, you can only take two electrons. Okay, and they also need to have a different opposite spin so that the charge or the magnetic field will cancel each other out. Okay, here's the diagram. So if you look, each of these arrows will represent the direction of the electrons. And also another thing too, you have this little funny uh, or order of filling the subshells. Now, how do we come to this organization? Is this because if you look back on 2 slides earlier, you notice that you're supposed to fill the shells at the lowest energy level first, right? So in this case, let me hide this because it's taking up space. So in this case, you're going to fill up 1s first. That's the lowest energy. Then it's 2s, and then 2p. Okay, so far so good. Seems to be making sense. Then you come to 3s. Okay, and then you have 3p. Now, instead of going to 3d, those orbitals, what you notice is that, oh, 4s, actually the orbitals at 4s is actually lower energy level than 3d. And then you have 4p, and then you have 5s, and then 5s, it has lower energy level than 4d. So because of that, you actually have to fill out the subshells in this particular order. Okay, so 1s, 2s, 2p, 3, like this, and then 4p, and then 4p, and then go down this here, this, and then you go 3d, and then 4. Oh wait, from left to right. Yeah, so going along this way. So now let's do the first one together. So in this case, krypton. Krypton is 36. So electron configuration is a list of subshells in order of filling the number of electron in that subshells known as a superscript. Okay, so in this case, let's draw this out first. Now, what I normally do is I draw this out first, so you kind of see how it looks like. So let's go with, so krypton, you have 36 electrons, right? So I'm going to use this a lot to help us. Now, so first of all, you're going to do the 1s one because that's the lowest level. You have 1s, right? So in this case, you have 2 electrons here. Okay, now I come down to 34 electrons. And after 1s, I go with 2s. Now 2s have 1 spot, so 2s. So in this case, it can take 2 electrons. Now I have 32. Now, after 2s, I go to the 2p orbitals. So 2p orbitals, as you notice, 2p have 3 subshells. Okay, 3 sublevels. Not 3 sublevels. 2p has 3 slots. So in this case, it can accommodate 6 electrons. So now I was going to do it the lazy way, but I should really model how it's supposed to be done. So you're supposed to spread out these charges first. Okay, electrons spin first before you fill them up. Okay. Okay, so now you have 6 gone. Now you have 26. Okay. So each of these pretty much symbolize an electrons. I put here about 10 of them already, so now I still have 26 electrons to go. So where am I? After 2p, I fill the 3s. So 3s. Again, 3s have 2 slots. No, 3s can accommodate 2 electrons, so draw like this. Now, 3p. 2, 3. 3p. 3p has 3 slots. Right. This is 24. Now I can take out 6 of them. So again, like this. So now I have 18. Okay. 3p. Am I correct? Yeah, that's here. That's here. That's here. That's here. That's here. Awesome. Okay, 3p. Good. So after I have 3p, now I go and do 4s because 4s is a lower energy level than 3d. So I have to fill those out first. So 4s. So I can take up to 2 electrons. Now I have 16 left. Okay. Now 3d have 5 slots here. So 1, 2, 3, 4, 5. 3d. Now this can accommodate up to 10 electrons. So in this case, again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons. So now I have 6 more. Okay. 3d. Now, last but not least, I go to the 4p orbitals. So 4p's. So 4p has 3 slots. 4p. Oh look, I have 6 electrons. This can accommodate up to 6. So yay! 1, 2, 3, 4, 5, 6. So I have all 36 electrons drawn out here. This is the electron configuration diagram. Now to write out the electron configuration, just like what was said here, listing of subshells in order, filling with the number of electrons in that subshell written as a superscript. So in this case, right now, I have 2 electrons here, 2 electrons here, 2, 6 electrons, 6, 2, 6, 2. I have 10 electrons here. I have 6 electrons here. So to write it neatly, 1s, 2s, 2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Okay, that will be the electron configuration of krypton. Now, if you look at krypton and think back in the periodic table, krypton is a noble gas. What do we know about noble gases? Right, it actually doesn't react with other things. It's inert. So if you look at the diagram, what can you say about the electron configuration that might potentially explain why it is inert? There you go. All shells and all the subshells are filled. Kind of similar to the idea when you learned about the Bohr-Rutherford diagram. You learn when you draw those things. It's like, oh yeah, all the noble gases have their shells full, so follow the octet rule, and they're happy. They don't need to do jack. This is the same idea. Okay, so you can still see using our quantum mechanical model of the atom, it still explains this property of the inert gas. So this is the part where I would like you to work on the next one, which is the rubidium, 37 electrons, okay? Rubidium, I think. And try to draw that, the electron configuration of that, okay? By the way, there's a shorthand way, so you just use a previous noble gas. But let's see if you can do the whole thing first, okay? Pause the video right here. Okay, so let's check our answers. Okay, was I correct? Yep, I am correct. And the rubidium one, if you draw it all out, it looks like this. And then the shorthand version, you actually just show the previous noble gas configuration and whatever shell. It makes sense because this is really just one more electrons. And you know, if you were looking at these shell here, after 3p, you have to go to 5s, okay? So that's the rule of how you draw the electron configurations. Pause here. Do you have any questions? Okay. So, example, write the ground state of the orbital diagram and the electron configuration of silicon. So you have to figure out what the atomic number is. Okay. You draw out the 9 boxes to show the 3 levels. Essentially, this is what I was doing just now with the longer one. And then when you put in the opposite arrows. So again, this is pretty much how I've done this, but you're using the ground state orbital diagram. So you kind of noticed earlier too, when I was drawing this, I was always drawing, when I was filling these out, I always draw the up arrows first before I filled in the other ones. That's just a rule, okay? That's just a rule, so you always do this first. And you notice you always filled out all the shells before you start pairing them. You don't want to have like an empty shells here like this one. This could be spread. Keep in mind they're electrons. In some ways, electrons, same charge, don't like to be close together. Think of it this way. Now, valence electrons versus core electrons. Now, so we kind of I'm pretty sure you have learned this back in grade 9 or 10 when talking about valence electron versus core electrons. Okay, so valence electrons are the electrons as the highest level, highest energy level, or highest orbitals. Now we learned about subshells and things like that. So the highest subshells, and the electrons that's the lowest one are called the core electrons. So usually it is the valence electrons that actually determines what are the chemical and physical property of a certain element, okay? The number of them. So if you remember from your grade 9 and 10 chemistry, you'll probably remember that, well, yeah, this column, lithium, has one valence electron, this one has two, this column has three. Oh, look, if you look here, you actually see that, oh, that has three. Same thing here. So this one has four valence, 5, 6, 7, 8. So it's really the number of valence electron that determines the chemical and physical property of an element. Okay, just a little review. So the valence electron. So this one, it is the highest principal energy shell, contains the fifth. So this one has one valence electron and 36. Now krypton. Now, krypton, again, is the same thing. You have 8 valence electron because the highest principal energy shell. So we're talking about the biggest number, okay? The biggest number. We're not, even though this have higher energy level, this is not the same thing, okay? You're talking about the subshells. Okay, you're talking about the largest principal energy shell. So this still have 6 valence electrons. So we have six electrons, so it's 8 valence electrons, so it's 8. So in some ways, this explain again, just like what I was saying earlier about this 1A column has 1, 2, 3, 4, 5, 6, 7, 8 valence electron. Something you learned before. Now you actually see it in this electron configurations. Now because of what you learned, we're actually gonna move into be able to explain those periods and trends a lot better. So if you're talking about the same period of things, you are talking about valence electron in the same shell, okay, same energy shell. Keep in mind you're talking about the larger number, okay? The larger number. When you go from left to right, valence electron increase by 1. You're talking about the same group. Keep in mind, group is the one that go up and down. That has the same number of valence electron. We talked about that just now. Group number equals to the same number of valence electrons. So if you look at the slide just now, this 6A will have 6 valence electron. Okay. You should have learned this back before. So this is also the reason why some people will say this is one way to say this is the S block. This part is a P block. Transition metal is generally D block because you actually use and go to the D orbitals or D subshells. And this here is the F block. This explains furthermore why our periodic table is organized as such. Okay, Mendeleev organized it according to the chemical properties. Now we know more about the atoms and how the configuration. It kind of continue to kind of like, hey, look, it's Mendeleev. What he noticed still makes sense. We just have much better math to reinforce or make it more concrete. So let's see. In our configuration is the same as before. To get the outer electron configuration, use the previous one and the loop through the next period. So basically, if you don't want to start from scratch, you can always just go to the nearest or the just the previous noble gas, and then you draw that way, okay, as PD things like that. The D block is always one energy shell below the period number, and F is two energy shell below. That's just a diagram of showing that. Now, in some ways, it's a lot of practice. So do a lot of these practice and the practice questions on how to draw or how to write out the electron configuration of each element from the periodic table. So, what's so good about this quantum mechanical model? Again, we show that the property of the elements is determined by the valence number of valence electron, just like you previously learned, as well as the different elements of the same column has the same number of valence electron, and they show similar properties, just like what you learned previously. But right now we just have better math to prove it. Again, this was my question earlier about krypton. Why are they so inert? Because all their subshells are full, okay, based on the electron configuration. So, stable electron configuration and ion charge. So, now metal form cations by losing enough electron to get to the same. Non-metal like to gain electrons to go to the same electron configuration as the noble gas. It's very similar to what you learned in grade 9 and 10, why metals become positive ion, the non-metal becomes negative ion, so that they look like the noble gas. Exceptions to this rule: stability takes priority. Okay. Sorry about that. Just have to turn that off. So in this case, this here, okay, KCr, okay, chromium. Why is it that chromium instead of, now this is actually a very interesting situation. Why is that? Okay, why is it that if you follow the rule of that I just showed you, you would do this, but actually, in fact, you have to do that? Why is that the case? Okay. Electron configuration of copper. Again, copper is 29. So if you follow the rule that we did earlier, 4s, you should fill that out first before 3d. But why is it that you don't do this, you do this? Okay. The hint here is stability of orbitals. Filled orbitals is more stable than half-filled versus neither. So if you look back, I think one of the reasons why it is the case, look back at this diagram. Keep in mind you're talking about 4s and 3d orbitals. 4s and 3d orbitals. If you look here, what do you notice? And why do you think that is the case of you would actually rather fill this one first and rather having it half fill? So pause, write down what you think the answer is, and we'll talk more, okay? So this video, again, this lesson summarized how we develop our understanding of the atom from the Bohr model all the way to the quantum mechanical model. And also in the second video, we talked about how do we figure out the electron configuration of each element. And based on that, how do we explain the properties of different elements on the periodic table. So I hope this is helpful, and we'll see you next time. Bye.